Well, thank you very much for sticking by for the second half of the day's seminar. So I'm Tom. I'm a second-year PhD student, and my supervisors are John Goff at the Royal Holloway University of London and Lucille Mongeon-Thor. I apologize for that pronunciation here at the ILM. So I'm going to focus mostly on magnetic diffuse scattering, at least for the first half. So what it is, how we can identify it, and what are some experimental conditions or things that we need to consider to get good data. And we'll obviously talk about polarization analysis because it's the absolute best tool to isolate our diffuse scattering data. And I will go a bit into more detail on some of the concepts that we've already seen. I will talk about longitudinal spherical polarization, mostly the instruments, and I will focus especially on the longitudinal part. And then I will finish with a brief talk on inelastic scattering using polarized neutrons. So what is magnetic diffuse scattering? Well, let's consider first a ordered system, such as the one shown here. Such as the one shown here, where we have a perfectly ordered system, and all the spins are pointing in the same direction, and we have 2 spins per unit cell. In this case, we have infinite long-range order, or infinite periodicity, or in other words, infinite correlation length. So we're going to have something very, very sharp in reciprocal space, which is our magnetic Bragg peaks. If we then go to the opposite case, everything is completely disordered, and the spins come pointing any direction. We have purely incoherent scattering, and we have no structure in reciprocal space. We only have the smooth decay with Q, which represents our single ion magnetic form factor. So if this was an ideal paramagnet, this would be a great way to compute experimentally the magnetic form factor. But in between these 2 extreme cases, we have the correlated disorder system. This is a system where we still have an average structure, as we will see in a minute. I mean, you can see already that we have 2 spins per unit cell, but we still have some disorder because we don't have a periodicity. We don't have the same arrangement of spins in each unit cell. So because we have an average structure, we recover our magnetic Bragg peaks. However, these magnetic Bragg peaks are much broader than compared to the ideal case. And this is because now we have a much short range order, or a shorter correlation length, and the correlation length is inversely related to the magnetic Bragg peak width. But on top of this, we also have some extra scattering in between the Bragg peaks, which is given due to the presence of this disorder. And this extra scattering is the magnetic diffuse scattering. Now, this is for a system where we only care about the spins, but we have the exact same scenario for a nuclear counterpart. So simply change the spins by ions, and you would find also some scattering in between the Bragg peaks. Okay, that's weird. Yes. So this is great because this means we can actually separate our scattering into our structure into 2 components. We have the average structure, which is given by simply taking the average of all unit cells, and this gives the static correlations, and it's also what gives experimentally the Bragg scattering. The problem is that, for our example here, this is our average unit cell, and we effectively see half a spin at each unit cell position. So what Bragg scattering is seeing is half a spin, and that's not correct. We cannot have half a spin. We have full spin or no spin, and this is where the diffuse scattering comes into play. So diffuse scattering is represents the local fluctuations, which you can understand them as the fluctuations from the ideal. And this diffuse scattering will actually give us the full picture. So it will tell us that, in fact, no, we do have 2 spins per unit cell, and on top of this, the spins can only be at 90 degrees for this particular example. So you can see the importance of diffuse scattering because it actually gives us the entire picture. Before I forget, this is the total spin density, so equivalent to the rho for ions. So I mentioned we can get diffuse scattering due to correlated disorder, but we can also get diffuse scattering due to many other circumstances, such as thermal scenarios. So we are close to the magnetic phase. This particular example here is for the presence of missing spins or simply the reduction of the momentum of spin. So a terbium, this is the terbium is the magnetic ion, the one that has spin. And if we go to the stuff case, which for this particular system, stuffing means removing oxygens, and the effect of removing an oxygen is reducing the momentum of the terbium. You can see we have a huge amount more of magnetic diffuse scattering. So what do we care about these systems? Well, because there's a bunch of new magnetic states, very interesting states that we can study. Some of the more popular ones, or one of the most studied ones, is the geometric frustrated systems, in which the spins cannot satisfy all interactions. So you might have, for example, an interferomagnetic exchange interaction, and two spins might be interferomagnetic, but it might be with respect to the third spin, that interaction might be ferromagnetic due to the geometry and so on. Many of my examples are on frustrated systems, so I'm happy to talk more about them at the end. So what are some things that we need to consider to get good data? Well, this is obviously more from an experimental point of view. But one of the first things, and this is actually a positive, is the fact that the diffuse scattering is delocalized in reciprocal space. As you can see from this example here, that we have relatively high intensity in between the Bragg points. And this is good because many times many neutron instruments need to sacrifice flux in favor of high Q, but here we can actually sacrifice Q resolution in favor of flux. And as we will see in a minute, that is a very good thing. Another thing to consider, again experimentally, is that we need to satisfy the quasi-static approximation. And what this approximation states is that the energy that can be transferred to and from the system must be smaller compared to the incident energy of the incident neutron. And why is this? Well, you might remember when we do a diffraction experiment, the intensity that we measure is actually intensity integrated over all energies. And what this upper limit is telling is that we are transmitting an infinite amount of energy from the neutron to the system, and this is obviously impossible. So a more correct way to put this is by saying that our cap, our maximum energy transfer, is the incident energy of the neutron. But this gives us a new problem, and this is the fact that if our incident energy is too small, then we might miss some spectra. We won't see the full diffuse or the full diffraction picture. You see in this schematic here, if our incident energy is at around this minimum, then we won't be able to integrate over everything because we will miss this this peak here at higher energies. So how do we choose our incident energy? Well, this depends on the system. It depends on if it's a fluid or a liquid, if we care about the nuclear diffuse scattering. For magnetism, or for magnetic diffuse scattering, the characteristic energy of the system is given by the Curie-Weiss constant. Curie-Weiss constant is a measure of the net magnetic interactions, and it's a temperature, but you can transform it into an energy, and you can very easily, you can measure it with a magnetometer at a lab. So this is a manganese oxide, which has a Curie-Weiss temperature of about, I think it was 115 or something like that, 115 Kelvin, 116 Kelvin, 116 Kelvin. You can see if our incident temperature is much smaller, then we don't see the full picture. We simply see the sort of artifacts which are not actually there. It's just part of the picture. But if our incident temperature is much larger, so 650 Kelvin for this case, then we do see the full picture, and you can see it matches quite well with the model. Now, when it comes to rare earth oxides, so the terbium example that I showed before, generally, I believe the Curie-Weiss constant is actually quite low for those kind of systems. Now, unless you deal with really, really cold neutrons, you don't worry much about them. But for transitional metal oxides, you do need to be careful. They can go up to temperatures of 500 Kelvin or even more. The last thing to consider when doing experiments is the fact that the intensity of the diffuse scattering is low. The magnetic diffuse scattering is very low. You can see this example data, which is another frustrated system, geometrically frustrated system. You can see that our intensity is quite low. This is the same for the structural components, so the nuclear diffuse scattering, but that one is usually higher in energy. sorry, higher intensity. So things you can do is use larger samples. Used to be the joke in the past was that with neutrons, the size of your sample must be the size of your thumb. That's the rule of thumb. Obviously, that's not much the case nowadays because there have been improvements, but it's something to consider. And if you have a large sample, then better. Now, I think do is consider all possible sources of background and error, and then correct them in the data processing. But the absolute best thing that one can do is use polarized neutrons. So if we do experiments at low temperatures where the magnetism is important, then generally speaking, we measure a combination of the magnetic and the nuclear scattering. So the magnetism, which is interaction of the neutron with the spin and unpaired spin electron, and the nuclear, which is interaction with the nuclei. But on top of this, we also have incoherent scattering, which you might remember from other seminars. And incoherent scattering can be separated to an isotope, which is the random distribution of isotopes along the sample, and spin incoherent, which is the random distribution of the nuclear spin states. The nuclei also have a spin state, and the neutron can interact with it. Now, these two components cannot be separated, or at least not experimentally. You need to do some data processing, but we can separate these three blocks using polarized neutrons. So we already saw how polarized neutrons work. So I'm just going to build up on some concepts that we already seen. And with polarized neutrons, a polarized beam is a beam in which all the neutrons have the same spin state, and that spin state is pointing along the same direction. And to achieve polarization, we use a polarizer. And here's where the problem of flux comes into play. To achieve polarization, we effectively remove a bunch of spins, a bunch of neutrons, and this can cause a huge reduction in our flux. So if you want to, want to use polarized neutrons and also have high Q resolution, you just end up with no neutrons, and it's more difficult. There's obviously been a lot of improvements, and I'll show an example of one of those in a minute. So just briefly, two different types of polarizers. We've already seen how polarizers work, so this is just common examples at the eye level. The first one is a polarizing filter, in which we use the spin-dependent property of the absorption cross-section of the helium. So the spin of the helium and the neutron are anti-parallel. The absorption cross-section is large. If both of them are parallel, the absorption cross-section is low, and the neutron goes through the sample or through the cell virtually unchanged. Another very commonly used technique is using supermirror, in which we make use of the spin-dependent property of the critical angle of the neutrons. And so now we have two critical angles, one for the spin up and one for the spin down. And we can set up our supermirrors so that the neutrons reflect at an angle between these two critical angles, and we will have an almost perfectly polarized beam. So they're obviously more like polarizing crystals, but I'm not going to go into detail of those. So we already saw that with polarized neutrons, we have two types of scattering, or two new types of scattering. Non-spin flip, in which the spin state does not change after scattering, and spin flip, in which the spin state does change. We can actually relate this kind of scattering to the relation between magnetization and the polarization. So if our polarization is parallel to the measured magnetization, then we only have spin flip scattering. And if these two components are perpendicular, then we only measure non-spin flip. A more correct term here might have been putting the component, so the X component, the Y component, or the Z component. But this gives you an idea on how we can differentiate them both experimentally. So the most basic type of polarization analysis that we can do is uniaxial polarization analysis, in which, as you might remember, we only measure the polarization before and after scattering along a single direction, along a single axis. And you might remember that the non-spin flip scattering always contains the nuclear part, while the spin flip only contains the magnetism. And this is true, but there's also extra components that we need to consider. First of all, the isotope incoherence. Now we also need to consider that, but that is always in the non-spin flip. Apologize for the noise, there's a train coming by. We also have the spinning coherent scattering, in which we have 1/3 of the component in the non-spin flip scattering and 2/3 in the spin flip scattering. And then the magnetization or the full magnetic scattering can be either fully in the spin flip if the polarization is parallel to Q, or 50-50 in the non-spin flip and spin flip if the polarization is perpendicular to Q. So uniaxial polarization analysis is good. It's a very, very useful technique, but it's not always great because you can see that our magnetic scattering is combined with the spinning coherent. And as I will show you an example in a minute, spinning coherent can actually be quite significant. And this would engulf our magnetic diffuse scattering, which is what we're looking for. We want to subtract and get good diffuse scattering data. So the best thing to do is simply measure the polarization along all directions, along the X, Y, and Z direction before and after scattering. This is usually called XYZ polarization analysis. And depending on the instrument, we have two types of polarization. Depolarization, oops, okay. The reason for this is because depolarization is not a value, not a scalar, it's actually a vector, as you might remember from other seminars. And the polarization is a vector which we can point in whichever direction we want. And we can relate our initial and final polarization through the polarization tensor, shown here. Now, if we only have access to the diagonal components, then we effectively have longitudinal polarimetry. And we can do this kind of analysis with instruments such as D7, which I will talk in a minute, here at the ILL, and LET at ISIS. But if we want to have access to the off-diagonal components, then we need spherical polarimetry, where we can, this is some examples of instruments at the ILL. In this case, we need a special equipment called a cryopad, which I'm not going to go into detail because I don't have time. But with cryopad, effectively the sample environment is zero field sample environment. And that is crucial because otherwise external fields might depolarize our beam. So you might be wondering, how is that we have extra polarizations along different directions? I mean, obviously, if our polarization is along the X direction, we only have spin flip up or down, so 180 degree rotation. So how is that we have extra polarization along different directions? Well, this is because if we expand our inelastic scattering equation, or double differential cross-section equation, with polarization, in this case, polarization is not necessary, but it just makes things a bit clearer. If we expand this, then we have a bunch of new terms. So we have the nuclear term, which is the term that we all know and love. Then we have the non-chiral pure magnetic terms, and these are terms that do not create polarization. That simply flips the neutron up or down, so a precession of 180 degrees. But then we have an extra magnetic, purely magnetic component, which is the chiral magnetic term, and this term actually creates polarization. It creates polarization along the Q vector. Yes, so this term will only appear if our polarization is parallel to the Q vector. So this is a case where to measure this, you absolutely need triple axis instrument, which is the case for spherical polarimetry, because you can very nicely always align your polarization with your Q vector. But we also have this final term, which I actually find very interesting, which is the nuclear magnetic interference terms or hybrid terms. And these terms are effectively the coupling of the nuclear and the magnetic contributions. You might remember from the last week's seminar that the potential can be separated into a sum of the nuclear and the magnetic potential. And thus, when you square those terms, you're going to have mixed terms, and that's where these terms come from, that mixing of the potentials. So these two terms create polarization, while this third term actually rotates polarization along M, along the vector M. So again, this is the type of thing that you would ideally want to use spherical polarimetry to be able to see this extra components. So I'm not going to go into, actually, before I forgot to mention, with spherical polarimetry, I'm not going to go into much detail because we already saw that in previous seminars, but I do want to talk about longitudinal polarimetry because it's a very nice technique. So this are the Stark equations, I think they're pronounced. I'm not going to go into detail here, but you can see how we now have 6 different intensities. So the non-spin flip and spin flip scattering along the X, Y, and Z direction. We have 6 intensities and 3 different incognita. And despite having, more terms, we are still satisfying that 1/3, 2/3 rule of the spin coherent scattering and that nuclear only non-spin flip rule that we had also in the uniaxial. So everything translates very nicely from 1-dimensional to 3. So one of the absolute best instruments to perform longitudinal polarimetry is D7. So D7 is an instrument that the ILO. It's actually quite a unique instrument. There's another one like it called DNS in Munich. But D7 has been optimized for longitudinal polarimetry. So D7 has a supermirror as a polarizer. And in this case, is a Bender supermirror. And this is because we are focusing the beam of neutrons just before arriving at the sample. And this is a way to increase our flux. I mentioned the problem with the flux here. Well, in this case, we can have 3 different beams of the same wavelength and sort of converge them both, all 3 at one point. Then we have the flipper. In this case, it's an SI flipper, which, as you might remember, is the flipper is simply used to change the spin state of a neutron from up to down and vice versa. And in this case, the flipper is used to change from spin flip scattering to non-spin flip scattering, as I will show an example in a minute. Then we have the sample environment, which can take either an orange crash pad or a dilution fridge. But most importantly, the sample environment has a set of X, Y, Z coils, which can produce magnetic fields along the X, Y, Z direction, and with which we can produce longitudinal polarimetry. So you can see how with this instrument, it's not possible to use spherical polarimetry because you're effectively submerging our entire sample environment in a magnetic field. And it's not possible to have part of the magnetic field before the sample and part of it after. So this is why this instrument is exclusively for longitudinal polarimetry. Finally, we have a set of analyzers, supermirrors just before the detectors, so that we only detect the spin down, sorry, we only detect the spin up neutrons. So this is, to change to, there you go. So this is an animation of how D7 works. But I forgot to say that D7 has a weak or a guide field, which is a field applied, magnetic field applied the Z direction along the entirety of the instrument. And this is used to keep the beam polarized, otherwise it would depolarize due to external fields. So we start with a beam of neutrons with all wavelengths and all spin states. We select a single wavelength, D7 has the option of 3 wavelengths. The guide field aligns our spins. The polarizer gets rid of the spin down neutrons. And because the flipper is on, we flip from all up to all down spin neutrons. With scatter, we have some spin down and some spin up. And the analyzers will remove the spin down neutrons and we will only detect the spin up neutrons. So you can see here, because the flipper was activated, we measured spin flip scattering. We went from 7 down to 4 up. If the flipper would have been off, then the intensity would have been not spin flip from 7 up to 4 up. Now, obviously, if we would have had a second flipper after the sample, then we would have been able to measure also the other 2 kinds of scattering, so down to down and up to down. But D7 is a time of flight instrument, so we can, or sort of time of flight instrument, so that would not be possible. That's more for triple axis instruments. Okay, so this is an example of longitudinal polarimetry. So this is a Volerite, which is a type of cadmium antiferromagnet. And it's actually quite an interesting example because you have a combination of low dimensionality and geometric frustration. It doesn't really matter. What I want to show here is the difference in scale of the spin coherent and the magnetic scattering. So this is a case where uniaxial polarization would have not been enough, because we would have had a combination of the red and blue curve, and it would have been impossible for us to separate the diffuse scattering. Now, obviously, this is a sort of special case because this particular sample has a lot of hydrogen, but there are some samples that the spin coherent scattering is usually quite low and sometimes can be ignored. But when you're dealing with diffuse scattering, which is very low in intensity, then the best thing is simply to use polarized neutrons and separate everything. So I talked a lot about polarized neutrons for diffuse scattering, magnetic diffuse scattering. You might be wondering, can we use polarized neutrons for inelastic scattering? The answer is yes, but it's not always necessary. Both magnetic excitations and phonons behave very differently. Phonons increase in intensity with higher Q and higher temperature, while magnetic excitations decrease in intensity with higher Q and higher temperature. And on top of this, we have that with neutrons, we have that restriction that we're only sensitive to the perpendicular part of the magnetization. So for most experiments, you can usually do experiments at different temperatures, or simply measure a wide range of Q, and you can then, during data processing, look at different regions in Q space, and you can nicely separate the different components. But as you might remember from some slides ago, we have those hybrid terms, and in that case, we would have the magnetic and the neutral contributions at the same Q locations, and that's points where the polarization analysis of polarized neutrons are extremely necessary. So we can perform inelastic scattering in all of the instruments that I mentioned before. So D7 has a chopper that can be activated and transforms the instrument into a time-of-flight instrument. And obviously LET is an instrument of ISIS, and ISIS is a spallation source, so it's naturally a time-of-flight instrument. For the spherical polarimetry instruments, we need to use triple axis. At the moment, CryoPad 2 and spherical polarimetry is very much focused to triple axis instruments, though there is some talk of some ideas on how to make it time of flight, but for the moment, spherical polarimetry is very much a triple axis instrument. So we can perform inelastic scattering experiments or inelastic spherical polarimetry, but not very good. I was talking with Karim, which is one of the local contacts from Ion 12, and my understanding from the conversation with her was that we can perform inelastic scattering with the diagonal components, but inelastic scattering with the off-diagonal components would be a bit difficult, and I don't think there's been any successful experiment yet. But with that, with the spherical inelastic polarimetry, we could do experiments to see maybe the chirality of spin waves. So this is an example of an elastic longitudinal polarimetry, where we have terbium, which again is another frustrated magnet. You can see most of my examples are from that. And this was performed, so this is the full diffraction data, and this is the elastic data. This experiment was performed with uniaxial polarization analysis, where this figure here on the right is the spin flip scattering. So in this case, spinning coherent was low enough that it could be norm. As you can see, down at about 0.35 MeV, which is effectively in the quasi-static regime, we have a very weak magnetic excitation, a local magnetic excitation, and it's actually very close to elastic scattering. But if we go to the full diffraction experiment, you can see that our intensities are actually quite high. So the diffraction scattering, I guess after subtracting the elastic, you end up with values of 1 to 2 units, while here our maximum is about 10 to the minus 3. So, and on top of this excitation would have been engulfed by these two elastic peaks. So this was a case where uniaxial polarization analysis and polarized neutrons were extremely necessary. But just a brief summary, we saw what magnetic diffuse scattering is and how it's present due to when we have correlated disorder. And the magnetic diffuse scattering is characterized by being delocalized in Q space and having low intensity. And on top of that, we need to satisfy the quasi-static approximation to be able to see the full picture and not simply some artifacts or some missing components. We saw that we can use polarized neutrons to separate all kinds of scattering, with which we can get very nice magnetic diffuse scattering, as I showed in my example. And we can use polarization analysis to perform inelastic neutron experiments. But it's not always necessary, because usually you can separate them nicely. And it's sometimes reserved for more specialized cases for when we have those hybrid terms that I mentioned. So thank you to finish. A thank you to all these lovely people, Ed for helping organize things, Andrew, Lucille, Karen, and Maxfield for the questions, and Joe, Goran, Ross, and Sean for letting me use some of the examples from some slides that they had. And that's all. Thank you very much. I'll be taking questions now.